Hey everyone, so this hopefully should be the last video on this topic of entropy and temperature. This one is going to be much more focused on calculations and doing some practice problems, as well as I'm going to end this video with a really good example of what you'd actually be expected to do on a test or something. All right. So before I continue, the one thing that I want to mention before I go back to the concept of entropy is the four laws of thermodynamics. Now, these are laws that you've definitely learned before. However, when we're going to talk about them now, we're going to kind of change a little bit what about the phrasing. So the first one, the zeroth law of thermodynamics. For anyone who doesn't know, a lot of times the zeroth law of anything, while thermodynamics definitely is the most prominent example, there are other zeroth laws. But usually a zeroth law is something that's created and written that it doesn't bring any new information, but it states something that has to be said in order for other things in the other laws to kind of build from. So you can almost think of this as the foundation that you don't actually see on the house. Everything else is all the other laws are built upon this. So the zeroth law of thermodynamics basically states that if two systems are in thermal equilibrium with each other with a third, then they have to be in thermal equilibrium with each other. Basically, another way of saying that is that if the temperature of system 1 and 3 and the temperature of system 2 and 3 are the same, then that means that the temperature of system 1 and 2 are the same. Again, it's something that has to be said. Of course, I very clearly recognize this, but it's just something that kind of tells us about the idea of equilibrium. And then the first law is essentially, or at least the the way that we're going to look at it is that heat is a form of energy. So you've probably seen this type of equation. Usually, the first law in I believe it's physics 126. You'll see it being written like this: that the change in internal energy of a system is equal to the heat added to the system plus the work done on the system. Uh, Basically, it's the same thing. It's the idea that heat is a form of energy and that energy is conserved. So that's really the interpretation that we're going to take from the first law. Now, the second law has two different forms. The first one is that if a closed system is in a configuration that is not the equilibrium configuration, the most probable consequence will be that the entropy of the system will increase uh, as a function in time. The idea, what this is really referring to, is that if the system is not in that most probable case, remember we mentioned that when two systems are in thermal contact, they're going to, when they start going towards that thermal equilibrium point, they're going to go to the most probable configuration of the accessible states. So this is just saying that it's going to go towards that most probable configuration. And that as it goes there, the entropy of the system will always increase. Another interpretation that we could think of this as is that it's impossible for any cyclical process to occur where the sole effect that heat is extracted and put into the form of work. Again, it goes back to the idea that there's always going to be the entropy increasing, that there's always going to end up being some energy being lost through a cyclical process. So this is useful more for energies. I'm sorry, not energies, for engines. In the idea that you have I kind of mentioned this before, that you have a system where it starts at one state, then it goes to another state, and it goes back to that first state. There's always going to be some energy being exhausted, and that it's basically impossible for us to just take heat from a system and then put it into the form of work. Um, and this kind of pretty much says that it's impossible to create perpetual motion machines, mainly because of the fact that in this second case that we mentioned, the entropy is not increasing. See, if the heat being extracted is equal to the amount of work being done, then the entropy of that system does not increase. So that's why this is a slight variation on this interpretation, because both of these are kind of saying the same thing, that any closed system, any process that we do, the entropy has to end up increasing. And then the third law basically says that uh, the entropy approaches a constant value as the temperature goes to zero. So again, that there is a lowest entropy level. It's not actually zero, but there is a lowest possible entropy level, and that occurs when tau is equal to zero. A lot of times you might see this G0 being referred to as the ground state multiplicity. So another way of writing the third law would be as this, a limit function, that as the limit approaches of temperature goes to zero, the entropy reaches some constant value. All right, so those are the 4 laws of thermodynamics. All right. Some of that stuff is going to reappear later on, which is why I'm just throwing that in there right now. So really quickly, here's a practice question where you can kind of practice a lot of this stuff. Pause the video, work on this stuff, and we'll go over in a second. All right, so they want us to figure out this for this setup. Now, if you remember, we had an equation that told us what the multiplicity, the total available states related to the max available states and the deviation factor. So what they're looking for is that deviation factor. So if we just writing down everything that we're given a bunch of the number of molecules, and we're also given the delta of how much the spin system's deviating from the ideal max most probable case. And the deviation is 10 to the 11th. All right, so what we have here, this is the equation that I mentioned before about the multiplicity at any point from the most probable related to the most probable multiplicity. And then this is the deviation factor. Based off of this, we're just going to take this coefficient part, divide it over, and then we're just going to solve for this part. That's really what they're looking for. So we plug the numbers in, we know what our delta is, we know what the number of molecules are, plug everything in, and we get e to the negative 4, or 0.0183. So what this basically says is that this is essentially about 2% of the max value of multiplicity available states. That's pretty much what it's saying. Here's the next part. You can pause the video, work on it yourself, and we'll go over in a second. All right. So now what we're going to do is we're defining S as being equal to 10 to the 20th. And what they're going to want us to do is figure out what needs to be multiplied by this so that it's equal to this term. So once again, we're going to start off with write down some of the things that we know. We know that S is equal to 10 to the 20th. We know that the number of molecules N1 and N2 are the same. And then we can also figure out what the peak values are for the half spin excesses. So what we have is this. So we know again that the max most probable configuration is going to be equal to the product of the individual ones. Now, since the number of particles, the number of spins is the same for system 1 and 2, and we also know that the peak value is going to end up being the same, we could just square it, and we end up getting this term right here, which ends up simplifying to this. All right, so what we're going to do now is come up with this equation. So we got an equation for this. Now we just need an equation for this, the sum of these products. So what we're going to do here Actually, I want to take one step back and explain a little bit more about why is S1 caret, that this most probable spin configuration, why is it the same for both systems? If you remember, our definition, our condition for the most probable configuration is that S over N for both system 1 and system 2 have to be the same. Since N1 and N2 are the same, that means S1 and S2 have to be the same at the most probable configuration. So I just want to state that really quick. All right, taking a step back, using this equation, this is just another definition for the total available states. So we know that the Gaussian approximation, which they actually say that we can use, the Gaussian approximation is given by this. So we need to figure out, what do we have to multiply this most probable configuration for the number of available states in order to get the total available states. So we just say that this most probable configuration is going to be multiplied by some variable x, and we're going to set it equal to this term. And then we'll just solve for x, plugging in what we have. So take this, divide it over. A lot of these things drop out. Like for example, we have a 2 to the 2n1 here. We have a we have this and this being almost repeated, though this is square root, this one isn't, but that's an easy fix. Then we also have this term, which a lot of things will end up dropping out. But when we start moving things around and dropping things, what we'll end up getting is this. So actually, I believe the e functions, yeah, the e functions actually do drop out as well. This is just the same as that. Again, having to replace some terms with what they kind of tell us up here. But then from here, I can then just simplify a little bit more, and I end up getting that x is equal to 8.86 times 10 to the 10 as the factor. So basically saying that the total available states is going to be this number times the times bigger than the number of states in the most probable configuration, which makes sense. While the most probable configuration will have the most available states compared to all the other ones, because of the large number of particles, there's going to be and the large variety in the half spin excess, there is going to be a much larger value for what we can get in total versus what the most probable configuration will end up being. So it makes sense that this number is going to be so big. All right, so then we want to know how large the fractional error is. So you can pause the video, work on this stuff, and we'll go over in a second. All right, so what they want is the fractional error. So basically the difference in the entropy with and without it over the total entropy. Another way of writing it would be like this. The entropy, regular sigma, is just going to be ln of the most probable configuration, while sigma prime is going to be essentially the total total available states. So plugging this all in, we can actually leave it like this for now before we simplify. That way we can actually start, dropping things. This, I know it's not super clear in how I wrote it, but this x actually is inside of the g. So I'll rewrite it in the slides. But because it's in the ln function, we actually have to separate ln of g1, g2 max and ln of x in both in the numerator and the denominator. And then from here, this will actually simplify because these top two parts will cancel out to be like this. So plugging in the numbers that we have, of course we have to actually figure out what, because we didn't have this number before, we're going to have to plug this in. So when we plug this in and take the ln of it, basically find the entropy of this, it simplifies to being this term. Um, so simplifying all this, moving things around, like I said, starting to plug the numbers that were given, we end up getting the fractional error in the entropy is 1.8 times 10 to the negative 21. So not super far off. All right. So this is the last thing that I want to talk about is the Einstein solid. So uh, a good thing that a common question that everyone's probably thinking about is what would I be asked on a test? What is the thing that you're going to have to be able to do? Are you just going to be repeating these equations? What is it? Now, one of the while that is very possible that you'll see some of the questions that you we've done in the class where, it's of course different scenarios, but same idea of hey, what is the total number of states available in this scenario, and then using that to find entropy. But another thing that you might end up seeing is something like this, where I'll give you a setup, a scenario, like an equation for the total available states. Much like how for the binary system, I gave you that the multiplicity function was n factorial over n1 factorial times n2 factorial. And then from there, you used something like the Stirling approximation in order to estimate that using a Gaussian form. And then from there, we found the entropy equation. Well, a common thing that you might see is maybe I'm giving you a different equation for the multiplicity function. Maybe instead of that, it's something different, but I want you to basically do the same thing. Use a Stirling approximation to come up with a Gaussian form, and then follow it through with finding entropy, and then follow through with finding something else that we've done or that we will do in this class. So this is a perfect example of what you would have to do, kind of repeating everything we did before, but with a slightly different scenario. So what an Einstein solid is a very common setup. Basically, this is done more so in sol- this is more with solids in physics. Um, Basically, the idea is that each of the particles can be thought of as little individual microscopic harmonic oscillators, essentially. Um, so in these systems, each one can only store a certain number of quantized energy units, essentially going back to the idea that these are quantum harmonic oscillators. Basically, we're going to say that the energy level between these units is going to be h bar omega. For those who don't know what the h bar is, h is Planck's constant, and h bar, I can't remember off the top of my head if it's 2 pi times h or if it's h divided by 2 pi. But it's basically a 2 pi, um, it's 2 pi off of h. And the lowest energy level that's available is going to be 1/2 of h bar omega. So if we pretty much write this out, if we have an Einstein solid and there's three particles, or another way we could say is three oscillators, these are all the variation of the combinations we can have. We could have 0 energy units, which would be 0 across the board. We could have 1 energy unit, which could either be put in the first, second, or third oscillator. We could have 2, which could be going 2 in each one individually, or we can have 1 and 1, 1, 0, 1, 0, 1, 1. And then 3 energy units, basically repeating the same thing we just did. Um, so from here, we can actually, just like we did before, come up with an equation for the total available states possible based off of how many energy units we have and the number of particles we have. So what it ends up being is we can actually write it like this. So this is one way that you could write it, but it basically turns into this, that it's Q, the number of energy units, plus n minus 1, where n's the number of oscillators, over Q factorial times n1 minus 1 factorial. Um, So, as we said before, we're not going to be able to use this for large particles. We can use this for, anything less than 50, but if we end up having a case where n ends up being really large, like in most solids, we're going to have to simplify this and estimate it into some Gaussian form, which is where the Stirling approximation is going to come in. So that's what I want you to do here. I want you to actually use this form of the Stirling approximation. This is another way of writing the Stirling approximation. But basically, I want you to take that Einstein solid equation with the factorials and simplify it or estimate it to look like this. Now there is going to be the hint that I want you to start with this slight variation on the equation, essentially getting rid of the n minus 1 parts. All right, so you can pause the video here, work on this yourself, and we'll go over in a second. All right, so what we're going to do is the same thing that we did last time. We're going to start off with our equation, with our multiplicity function. And what we want to do is we want to actually rewrite these factorials. So starting off, like I said, this is another way of doing the Stirling approximation, basically without the ln part. But what we can say is this, that if starting with this top, just replacing q plus n factorial in here, and then anywhere where we see the n, we just put q plus n. It ends up looking like this. And then we do the same thing for q factorial, and we don't really have to do anything for the n factorial. It's just what they gave us. But when we multiply these two, what we get is this. Just taking this multiplied by that. What we can do from here, however, is combine some of these terms so that it looks a little bit more like what was given. So if we combine the e's, the natural log e's, and we combine these square root terms, we end up getting this, which does look very similar to what we have in the numerator section. So combining it together, we end up getting this. We can drop these two e parts, and then we can combine this, the square root part, and we end up getting this. So far, if I look over here, it is starting to look like what I expect. So the next part is I'm going to want to have to split this up into a q power and an n power, and then I'm going to have to do something with these terms to kind of split this up. So we'll just continue with that. So further simplifying it, again, splitting this up into a q plus n to the q and q plus n to the n. We end up getting this. We can then split them up like in the separate terms. So far so good. The only problem though is that we have this square root part that's not working. Now remember, this isn't the Einstein solid equation. There's this term that I also have to include. So when I include this into here and bring it into the square root, I just square it, and now we can see that when I'm going to end up dropping this q plus n and one of these q plus n's, leaving me with 1 in the denominator, and this n drops one of these n's, leaving me with n in the numerator, and hey, look at that. We end up getting exactly what I'm looking for. So again, a really nice thing that we can do when they give us an answer is kind of constantly looking back and seeing what exactly we need to further change in order to get to the final answer. But this is a very good example of what you could expect to see on a test, where I can give you a multiplicity function for some random setup, and then you would have to use the Stirling approximation, either this one or the ln form, in order to come up with a function that doesn't include factorials. All right, so taking this one step further, now let's do another one with Einstein solids. So pause the video, work on this stuff, and we'll go over it in a second. All right, so we want to know how many different energy macro states are available for this. So we have two solids, each with n oscillators, and they tell us that the total number of energy units is 2n. So remember that the number of macro states is essentially going to be equal to q plus 1. Um, yeah, so that's pretty much it. If we look back in our examples before, when we had 0 energy units, there was only one possible state. When there is one energy unit available, technically we could have two of them. We could have 0 or 1 being distributed to everything. So there's always going to be one more than the number of energy units available. So all right, here. Now, I do want to actually go back to this one really quickly. So the reason why I'm saying that you can have 0 and 1 when you have one available energy state, because I just realized that it sounds a little weird, is because we have two solids. So like two systems. So if you have one energy unit, one system can have one energy, which would be which would be one macro state, and then the other one could have 0, or you could have it flipped and have one being 0, one being 1. If you had two, then one could have 0, one could have 2. One could have both of them could have 1, or 2 and 0. So again, it comes back to just kind of thinking about, well, how could I divvy up these two units, or these whatever number of units, between two solids? And the best way to figure it out is by looking at small cases first and then extrapolate the pattern from there. All right, here's the next problem. Pause the video, work on itself, and we'll go over it in a second. All right, so they want us to calculate the total number of microstates available. So we can use our approximation, since we're going to assume that the number n is an extremely large number, and we won't really be able to simplify that factorial equation. So we end up getting this. So this is going to be true for system 1, and it's going to be true for system 2. So what we can do is just say that it's going to be 2n for both n and q, since it's just the combination of them. And we end up getting this as our equation. So this is the total number of microstates available. Okay, here's the next part. You can pause the video, work on the cell phone. We'll go over in a second. All right, so here we're going to figure out what the number of microstates available is for the most probable configuration. So we can kind of use the same concept that we did last time, just replacing the half spin excess with the energy units, but it ends up being pretty much the same thing, that the ratio of energy per number should be, per particles should be the same. And since we have 2n energy units and we have 2n oscillators altogether, that we're going to end up being it's going to end up being equal to 1. So that actually ends up telling us that the value of energy units in Q1 has to be equal to the available energy units in Q2, or Q1 and Q2 being equal to n, because Q1 plus Q2 has to equal to 2n. So from there, if I just take the equation that we have for the total, the most probable configuration, and just use this idea that Q1 and Q2 are all going to be n, I end up getting this. So this is for the first system, this is for the second solid, and a lot of the ways where we can probably actually combine this and square it. Yep, we square it because Q1 and Q2 are the same. And then now we could just plug in n for all the terms, and it ends up getting me this. So this is the number of available states in the most probable configuration. Whew. All right. So another question, again, taking what we've done before, and we're just going to continue on with it. But pause the video, work on itself, and we'll go over in a second. All right. So this, I threw in a quick hint as to what I'm actually talking about. But what this is saying is we want to figure out the entropy of the system. Now, remember, entropy is based off of the number of available states. Now, as we shown in previous videos, the most probable configuration is pretty much the only setup of configurations that we should consider. Because in the real world, that's the most likely to occur. That we're not really going to be seeing things far outside of the most probable. But technically, we could also talk about all the available states. So what they use to kind of refer to these is over long time scales and over short time scales. If we consider short time scales essentially being things like what we would see in the real world, then that means that the available states that we're going to look at is only the most probable configuration. But if we go over large timescales, essentially multiple universes long, where an infinitely long amount of time, then what we can actually do is consider every microstate available. So I just wanted to point that out because in future questions, if I ask this question, I'm not going to include this hint afterwards. I'll just say, oh, what's the entropy over long time scales or over short time scales? So just wanted to point that out. So for part A, well, first we have to use the equation that we have. We know that the total number of available states is going to be given by this function. So the entropy is just the ln of this. So when I take the ln function of this, that splits it up into those two parts. I can then combine it, simplify it, do some calculations, use 10 to the 23rd for n, yada, 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 and I end up getting this. Now, you'll see why I didn't keep it all together. You'll see why I didn't just calculate the available states and then find the sigma. And you may notice that this is written in a slightly weird way. Again, you'll see in a second. But essentially, the total entropy is going to be some number times 10 to the 23rd minus this little 28.1. Now, over short time scales, when we're only looking at the most probable configuration, we're going to use this and take the ln of that. Again, splitting up into two parts. We end up seeing that this first part is actually identical to what we had before. So we still get the 2.77 times 10 to the 23rd, but now it's the second part that's changed. And now instead of it being 28.1, it's now 55.5. So the reason I had them separated is because the value of the entropy is going to be so drastically large that the difference is on the calculator at least won't pop up. So by keeping it separate like that, we actually will see that there is a slight difference between them. This is also one of the reasons why, again, we want to actually consider a difference in entropy rather than an absolute value of entropy. So we can actually see here that the entropy for the most probable configuration is a little bit lower than the total, but not significantly lower. All right, so this is just a lot of a summary of what we kind of talked about. You know, things like that every accessible state is equally likely and is available. So that's something that you have to kind of keep track of. The idea of how we take averages, like I said, this is going to pop up a lot as we continue on. The concept of ensembles, of being essentially a combination of all the systems occurring at the exact same time, or all the states occurring all at the same time. We talked about how we can find the total available states for a combined system. We defined the term of entropy and fundamental entropy. Conventional entropy and fundamental entropy. We came up with the definition relating to fundamental temperature and conventional temperature, I guess we could call it. And we also talked about how entropy is always increasing and all that stuff. All right, so this is your first problem set. It's going to be from chapter 2, and it's these 3 questions from the textbook. The due date is going to be provided on, I'm not yet sure if I'm putting the homework submission through Blackboard or through Google Classroom. I think I might use Google Classroom rather than Blackboard, but don't hold me to that. I'll make a comment in the remind later on about which one I'd rather prefer. But yeah, whatever date it says there, that's the date it's due. So most likely it's due a few days, probably like 3 days after this video is due. But these are the 3 questions that you're going to end up working on, pretty much doing a lot of the same things that we've sort of done in class, but now using slightly different starting points. All right. If you have any questions, please let me know. Otherwise, I'll see you later. Bye.